guys, it's Ms. Johnson here, and I'm here to bring you your 8-3 notes on graphing rational expressions. Just a brief look at a rational expression or an example. Let's just take a look at the functions we have graphed so far this year. Now, we're really familiar with linear equations. Linear equations are when we have the x to the first power and they give us a line there. Quadratic equations give us that parabola and they have an x to the second power. And square root functions are when we had a radical sign with an x underneath, and we've seen functions that look like that. That gives us this nice curve here that we have been used to seeing. They had the starting point and went in one direction. Other polynomial functions that we saw, we talked in chapter 6 about counting the degree. This one would be a degree 3. This one would be a degree 4. This one would be a degree 5. So just functions and what they look like, functions that we've seen so far this year. Now today we're going to be talking about rational functions. Let's just take a look at a brief example. It says a group of students want to get their favorite teacher, Mr. Domingos, a birthday gift. They want to plan to get him a gift certificate for a weekend package to a lodge in a state park. Their gift certificate costs $150. If C represents the function, if C represents the cost for each student and S represents the number of students, then the cost is the $150 divided by the number of students paying. So obviously, when we take a look at this graph over here, if I have one student that's paying, that means that that student has to spend all 150 bucks. Now, the more students that pay, the less amount they each have to pay. If 25 students pay, then you're down to only paying 6 bucks. If all 150 students that he has pay, then each student only has to pay $1. And you get this kind of curved function here. Take a note that it doesn't ever cross the x-axis, nor does it cross the y-axis. It just simply approaches them. Okay, so we're going to be graphing some of those rational functions today. Now, I want to start by giving you some terms to talk through. Rational function. A rational function is a ratio of two polynomials. A ratio of two polynomial functions. So I'd have some function f of x where I have a polynomial on top, p of x, and a polynomial on the bottom, q of x. Some examples, if I had f of x is equal to x over x plus 3, I have a polynomial of x on top and a polynomial on the bottom of x plus 3. G of x is 5 over x minus 6. Again, there's a piece on the top and a piece on the bottom. H of x, I have an x plus 4 on the top and an x minus 1 and x plus 4 on the bottom. So those are just a few different examples of rational functions and what they look like. And we've been looking at those the last few days. Now, continuity. Okay. Continuity. Continuity is where there are breaks in the graph. So the graph of rational functions may have breaks in continuity. You cannot trace the graph without picking up your pencil. Okay, so there's going to be some break. It's not continuous. It's going to have some place where it stops. Okay, breaks occur at values that are excluded from the domain. So that's important to know. Breaks are excluded from the domain. From the above examples, there are pieces of continuity where the denominator is equal to 0. So if I look at the f of x function, if I had an x value of -3, then I would have a break in continuity. So x can't equal -3 there. If for the g of x function, if I had a value of 6, then I would have a break in continuity because that would be 6 minus 6 is 0, and we all know that we can't divide by 0. Same thing with the h of x function. In h of x, I have two breaks in continuity. I have a break in continuity at +1 and also at -4. So two breaks there. Okay. Let's take a look at vertical asymptotes. For vertical asymptotes, this is one of the types of breaks in continuity. A vertical asymptote is a line that the graph of a function approaches but never touches due to the domain restriction. It approaches, but it never touches it. Okay, so it's due to the domain restriction, it will never touch that line. Okay, in that example, For f of x, x over x minus 3, the line x equals 3 is a vertical asymptote, and that goes back to that domain restriction. X equals 3 is your vertical asymptote there. And then the last term for today is point discontinuity. Point discontinuity, or you will hear us more commonly refer to them as holes in the graph. Holes occur when you have a value that's excluded from the domain, but it cancels out when the function is simplified. So if you look at that example that's given to you on your notes there, where we have f of x is equal to x plus 2 times x plus 1, x plus 2 on the top times x plus 1 minus 1 on the top, all divided by x plus 2. Okay, these two factors, x plus 2 over x plus 2, cancel out, and we've looked at that. But that still means that they were a domain restriction. So it canceled out when the function was simplified, but it's excluded from the domain. So where you get x is equal to -2, that becomes a hole. So wherever x is -2, which here's -1 and here's -2, that's my line, that's the point where it is on my line, I now have a hole. Okay, so that's where that comes from. And we're going to look at all of these things. Couple of reminders, and these are things that you've seen before. The denominator of a rational function cannot be 0 because division by 0 is not defined. So we cannot divide by 0, which means the denominator of a rational function cannot be 0. So let's take a look at example 1. In example 1, it says determine if any of the equations have vertical asymptotes and the values of x for any holes. So I'm finding the holes and I'm finding the vertical asymptotes. So first thing that I need to do, and you can write these steps down if it would help you. Here are these steps over here. Okay, the first thing I need to do is the same stuff that we've been doing all throughout chapter 8. I need to factor. So I'm going to start by factoring the top and factoring the bottom. So f of x, when I factor the top, I get x plus 1 and x minus 1, because that's a difference of two perfect squares. On the bottom, I have x squared minus 6x plus 5. I want a product of 5 and a sum of -6. That means I need x minus 5 and x minus 1. -5 times -1 is +5, and -5 plus -1 is -6. Okay, so now here's what we have. When we simplify this, I can get rid of the x minus 1 and x minus 1. It leaves me with x plus 1 on the top and x minus 5 on the bottom. So now here's what happened. The ones that canceled out, okay, the ones that canceled out end up being a hole. Oops, 1L, hello. It ends up being a hole. So the hole in the graph is where x minus 1 is equal to 0, because that's the factor that canceled out. When I set that equal to 0 and solve, I add 1 to both sides, and I get x is equal to 1. The one that's left over in the bottom, this one right here, this ends up being the vertical asymptote. So the vertical asymptote is where x minus 5 is equal to 0, and I solve for that, x is equal to 5. So your vertical asymptote is x equals 5. Your hole is x equals 1. Two domain restrictions there, one that's a hole and one that's a vertical asymptote. Let's do one more example together in number 2. In number 2, I am looking at the equation x squared plus 6x plus 8 over x squared minus 16. So again, I'm looking for any vertical asymptotes and any holes. I'm going to start by factoring. When I factor the top, I end up with x plus 4 and x plus 2. When I factor the bottom, I get x plus 4 and x minus 4. I can simplify that by crossing out the x plus 4. That ends up being x plus 2 over x minus 4. So there's my simplified expression. Then I need to look for the two things. For the hole, okay, the hole is the factor that was crossed out. that one right there. So my whole is where x plus 4 is equal to 0. Subtract the 4, and I get x is equal to negative 4. The vertical asymptote, or VA as you can abbreviate it, is what's left over in the denominator. So the vertical asymptote is where x minus 4 is equal to 0. I add 4, and I get x is equal to 4. Okay, so here's my whole. It's really important that you label these, by the way. Here's my vertical asymptote, because obviously we're finding two different things and they have two different meanings. Okay, that's going to be the end of our notes video for today. So please hop back to Schoology and see if you can take that Schoology quiz for me, and I will talk to you tomorrow. Thanks. Bye.